The lunar surface, a desolate expanse of gray regolith, currently represents an immense logistical challenge. Every kilogram of oxygen required for human respiration or propulsion on the moon must be launched from Earth, a payload costing tens of thousands of dollars. This dependence creates a significant barrier to sustained lunar presence. The absolute silence of the lunar vacuum offers no atmospheric solace, rendering Earth-supplied oxygen a finite and precious commodity. For humanity to truly establish off-world civilization, a complete break from the terrestrial umbilical cord is necessary. The primary engineering goal is off-world self-sufficiency for vital resources. Paradoxically, within the very dust of the lunar regolith lies an abundance of bound oxygen. Over 40% of the moon's surface material by weight consists of oxygen atoms, primarily locked within metal oxide compounds like ilmenite, an iron-titanium mineral, and various silicates. The critical task is to unlock this trapped resource. One leading strategy for oxygen extraction is molten salt electrolysis. This process involves heating lunar regolith to extreme temperatures, often exceeding 1600 degrees Celsius, which liquefies the oxide compounds. An electric current is then passed through the molten material, causing oxygen ions to separate from the metallic elements. As the electric current flows, pure oxygen gas bubbles out at the anode, ready for collection, compression, and cryogenic storage. Simultaneously, valuable metallic alloys, crucial for structural components and manufacturing, accumulate at the cathode. This dual yield makes molten salt electrolysis a highly attractive method. An alternative method employs hydrogen reduction. In this process, heated lunar regolith reacts with hydrogen gas, which chemically strips away oxygen atoms to form water vapor. This vapor is then condensed, and the resulting water is electrolyzed to separate the hydrogen for reuse and the oxygen for collection. The establishment of a viable oxygen economy on the moon necessitates industrial-scale operations. Automated excavation and processing units, powered by robust energy sources such as compact nuclear fission reactors or extensive solar arrays, must operate continuously. This transforms barren lunar regions into vital resource hubs. The operational system for an oxygen economy begins with automated rovers identifying and excavating regolith rich in oxygen-bearing minerals. These rovers, equipped with sophisticated geological sensors, transmit data to a central processing hub, optimizing resource acquisition and minimizing inefficient material handling across the vast lunar landscape. Excavated regolith is then transported to the processing plant, typically through shielded conveyor systems or autonomous cargo vehicles, protecting the raw material from solar radiation and micrometeorites. The rhythmic clang of machinery would define these processing centers, a stark contrast to the natural silence of the moon. Within the plant, the chosen oxygen extraction method, be it molten salt electrolysis or hydrogen reduction, operates continuously. Waste products, primarily spent regolith and potentially unused reactants, are either recycled into the system or repurposed as construction material, forming a closed-loop resource management cycle. The extracted oxygen, now in gaseous form, undergoes a purification and liquefaction process. It is chilled to cryogenic temperatures, typically below -130 degrees Celsius, transforming it into a dense liquid. This state dramatically reduces its volume, making storage and transport far more efficient for various lunar applications. Cryogenic storage tanks, often situated underground for thermal stability and radiation shielding, hold the liquefied oxygen. These tanks must maintain precise temperature and pressure, preventing phase changes that could lead to losses. This infrastructure becomes the central bank of the lunar oxygen economy. Distribution networks then transport the stored oxygen to various consumption points. This includes life support systems for habitats, propellant tanks for ascent vehicles and lunar hoppers, and potentially industrial applications like metal fabrication. A complex grid of pipelines and automated tankers would facilitate this crucial delivery. The byproducts, such as metallic alloys from electrolysis, are processed further for manufacturing structural components, tools, and equipment. The lunar industrial ecosystem aims to maximize resource utilization, transforming raw lunar material into finished goods. This cycle reduces dependence on Earth-sourced supplies for virtually all needs. The contrast between terrestrial oxygen production and lunar extraction is stark. On Earth, oxygen is abundant in the atmosphere, freely available for respiration or cheaply extracted from water through electrolysis for industrial use. The Moon offers no such atmospheric buffer, demanding a complete re-engineering of resource acquisition. Transporting oxygen from Earth to the Moon incurs astronomical costs. Each kilogram requires vast amounts of propellant to escape Earth's gravity well, navigate the vacuum, and perform a controlled lunar landing. Lunar In-Situ Resource Utilization, ISRU, dramatically cuts these costs, making sustained operations feasible where Earth reliance would make it impossible. Terrestrial mining operations often contend with complex geology, deep subsurface deposits, and stringent environmental regulations. Lunar mining, while lacking an atmosphere or biosphere, presents unique challenges. The fine, abrasive regolith, extreme temperature swings, and the ever-present threat of radiation exposure to equipment and personnel. The energy demands for lunar oxygen extraction are substantial, yet the Moon offers continuous solar illumination at the poles or the potential for nuclear power. This contrasts with Earth's diversified energy grid, highlighting the need for robust, self-sufficient power generation in the harsh, isolated lunar environment. Unlike Earth's carbon-based economy, the lunar oxygen economy operates on a closed-loop system where every resource must be accounted for and recycled. Waste is minimized and byproducts are actively converted into new materials. This extreme efficiency is a direct consequence of the immense cost and difficulty of resupply. The atmosphere of Earth acts as a protective shield, buffering temperature fluctuations and filtering harmful radiation. On the Moon, without such a shield, cryogenic oxygen storage and transport systems must be engineered for extreme thermal control and radiation hardening, a significant design departure from terrestrial counterparts. Ultimately, the lunar oxygen economy shifts humanity's perspective from Earth-centric resource dependency to multiplanetary self-reliance. It represents a fundamental engineering paradigm shift, transforming a barren celestial body into a source of vital elements rather than solely a destination for resupply missions. Despite meticulous engineering, lunar systems face inherent challenges that can lead to collapse. The fine abrasive regolith, for instance, infiltrates mechanisms, wearing down moving parts and sealing surfaces, potentially causing system failures in critical processing machinery or habitat seals over extended periods of operation. The extreme temperature differentials on the Moon, ranging from over 120 degrees Celsius in sunlight to below -170 degrees Celsius in shadow. Stress materials. Repeated thermal cycling can induce fatigue in structural components, pipelines, and cryogenic tanks, leading to microfractures and potential system breaches. Solar radiation and galactic cosmic rays continuously bombard the lunar surface. While shielding protects human habitats, it also degrades electronic components and insulation materials in exposed equipment. This slow, relentless erosion can cause instrumentation errors, communication breakdowns, and ultimately, operational cessation. Resource depletion, though perhaps less immediate, remains a long-term concern. While regolith is vast, specific high-yield mineral deposits might be localized. Continuous extraction from a single site could lead to diminishing returns, requiring relocation of heavy industrial infrastructure, a significant logistical and economic undertaking. The highly automated nature of lunar operations introduces new points of failure. Software glitches, AI malfunctions, or cyber attacks could disrupt the intricate dance of excavation, processing, and distribution. A single critical system failure could cascade, bringing the entire oxygen production chain to a halt. Reliance on specific energy sources, such as solar power, introduces vulnerability. Extended periods of lunar night, dust accumulation on panels, or even unforeseen equipment malfunctions can severely impact power generation, which directly cripples energy-intensive oxygen extraction processes, causing temporary but critical supply interruptions. Furthermore, the constant threat of micrometeoroid impacts, while individually small, can collectively damage exposed equipment, solar arrays, or pipeline networks. A critical strike could result in depressurization of storage tanks or irreparable damage to processing units, necessitating costly and time-consuming repairs. Despite these inherent risks, the establishment of a robust lunar oxygen economy remains an imperative for humanity's long-term off-world survival. The engineering challenges, while formidable, are precisely what drive innovation and the development of new resilient technologies and operational protocols. The successful creation of a self-sustaining oxygen production cycle on the Moon signifies a fundamental shift in humanity's relationship with space. It transforms the Moon from a mere waypoint or scientific outpost into a true resource frontier, a critical stepping stone for deeper exploration and settlement. This lunar infrastructure will fuel not only human habitats, but also advanced propulsion systems for missions to Mars and beyond. Oxygen, initially a life-sustaining gas, becomes rocket fuel, enabling greater payloads and faster transit times across the solar system, drastically reducing reliance on Earth's launch capabilities. The Moon, once perceived as barren and inhospitable, reveals its hidden potential as a vast reservoir of vital elements. The systematic extraction and utilization of its resources exemplify humanity's capacity to adapt and innovate, extending its reach beyond the terrestrial cradle through scientific and engineering prowess. This endeavor reflects a deeper drive, the instinct to survive and thrive beyond the familiar confines of Earth. It is a testament to the pursuit of self-sufficiency in the face of the universe's absolute indifference, a deliberate act of imposing order and life where none naturally exists. The rhythmic hum of lunar machinery extracting oxygen from rock is a testament to the expansion of terrestrial logic into the cosmos. It represents the conversion of raw celestial material into the very breath and fuel of human endeavor, asserting a foothold in the vastness beyond our home world. As the Moon's oxygen economy stabilizes, enabling permanent human outposts and interplanetary travel, what other seemingly impossible cosmic resources await the ingenuity of humanity to unlock across the boundless void?